Alright, here we are, 10-6, and we're ready to put a fork in this thing because I think it's just about done. Today, we're just kind of putting everything together, and we'll be discussing the hardest, probably, concept we have, or at least the thing that you have to memorize, which might be difficult. So, you're going to need full attention. Make sure you put away all the other things and make sure you're listening and not just writing down notes, because as we figured out by now, just writing down all the notes is not going to be helpful to you. A random variable is just any random events. When we talk about variables, remember those were those letters and the things that they vary, right? And so a variable whose value is determined by the outcomes of random events, like flipping a coin or whatever, right? Probability distribution. So I'm just going to kind of talk through these a little bit. Probability distribution, a function that gives the probability of each possible outcome for a random variable. The distribution ends up being when we're going to make these tables or histograms to show like how things happen. Binomial distribution is a type of probability where only two things can happen. And this would be the distribution, this would be the experiment, but in both terms it's a yes or a no, or heads or tails, you know, rain or no rain, that type of stuff. Two things are going to happen, and we'll get more in depth with some of this stuff as we go. Symmetric, don't forget, symmetric is, you know, cutting something in half, both sides look exactly the same, being symmetrical. And skewed, when we talk about these histograms, some of them are going to look like this. And you wouldn't say that that is symmetrical, so that's a skewed histogram. Alright, let's get into some of this other stuff. A probability distribution is a function that gives the probability of each possible outcome for a random variable the sum of all the probabilities always has to equal 1. So if I say, what are all the things that could happen, when you think of all the different things that could happen in a possibility and you put them all together, what's the percentages? When you add all those percentages together, you should have 100%, because those are all the different things that could happen. Alright, let x be a random variable. Let x be a random variable that represents the sum when two four-sided dice are rolled. A four-sided dice. So the first thing we have to do is think about what would a four-sided dice look like. It would not look like this. That's for a six-sided dice. A four-sided dice would have things like 1 and 1, or 1 and 2, 1 and 3, 1 and 4, and you kind of get the idea. That's where it would stop. And then we'd keep going, and we'd say, alright, you could have 2 and 1, 2, and so on and so forth. So we've already kind of set this up down here. You could get a sum of 2, sum of 3, 4, 5, 6, 7, or 8. There's one way to get a sum of 2, that would be that 1 and 1. There's two ways to get a 3, that would be a 1 and a 2, or a 2 and a 1. There's three ways to get a 4, 1 and 3, 3 and 1, 2 and 2. Four ways to get a 5, 2 and 3, 3 and 2, 4 and 1, 1 and 4. Three ways to get a 6. So 5 is the most popular number here. Unlike over here where 7 was the most popular outcome. Right? 7 was the most popular outcome on the 6-sided die. This is a 4-sided die. So you have 6, 7, 8. All right. How many different outcomes are there total? Well, 1 plus 2 is 3. 3 plus 3 is 6. 6 plus 4 is 10. 10 plus 3 is 13, 14, 15, 16 different things that could happen. Alright, so your chances of rolling a 2 would be 1 out of 16. Your chances of rolling a 3 would be 2 out of 16 or 1 out of 8. And you have 3 out of 16 here, 4 out of 16 or 1 out of 4, 3 out of 16 here for the 6, 2 out of 16 or 1 out of 8 again, and then 1 out of 16. So those are all the different possibilities. If I were to graph that, what I might do on my probability over here, these are generally percentages, these lines as they go up. Okay, down on the bottom I'm going to put 2, 3, 4, 5, 6, 7, and 8. And sometimes we can do with this, instead of making them percentages, maybe what we make them is fractions. So we could make our first line 1/16, and then this would be 2/16. This line would be 3/16, 4/16, and 5/16. Alright, so it just makes it easier for us to draw our histogram. So because each line will then represent another 16th that it could be. So you have 1, 2, 3, 4, and then back down 3, 2, and 1. Now, some things we would say about this, because we just learned some new words. We would say that this would be symmetrical, certainly symmetrical. So I could draw that line right down the middle of it. It would cut it in half. Some things that we know, not skewed, and that's how you draw those histograms. Not super easy, but I'm sure you guys will be able to handle it with a little bit of practice. I don't know why my whole picture is not moving right now, but we'll work without it. Interpret a probability distribution. All right, let's read through this. Use the probability distribution in example 1 to answer each question. What is the most likely outcome of rolling 2 dice? Now, remember we're talking about rolling 2 dice that are four-sided dice here that they want to talk about, because they're talking about example 1, so that makes it a little bit confusing. The greatest for x is going to be the number 5, right? So the most likely outcome when rolling 2 dice is a sum of 5. That makes sense. The probability that the sum of the 2 dice is at most 4, okay, very, very interesting. We're at most 4. So that would mean x could equal 2, so the probability of x equaling 2. And really we're talking about or when it's at most 4, because you could get a 2 plus, see that's or you could get a 3 plus, or you could get a 4. That's a probability of at most 4. So when we're doing the different probabilities, the 2, remember, was 1 out of 16, and the 3 was 2 out of 16, and I'm going to leave these in 16ths right now, and the 4 was 3 out of 16. So I have a total of 6 out of 16 total for that situation. Hopefully that makes sense. You guys have a checkpoint on this page right here. So on this checkpoint, I'd like you guys to take a minute, try it. Pause right now and try it. Alright, welcome back. Let X there, you guys knew was X, A, B, C, and D, right? And A, there's 7 ways to get an A because there were 7 blocks that were A. And there were 3 ways to get a B, and there were 6 to get a C, and 5 to get a D. And I'm sure we were all able to get at least this far. Now there were 21 blocks total, so I had, my probability was 7 out of 21, which is 1/3, 3 out of 21, which is 1/7, 6 out of 21, which reduces to 2/7, and 5 out of 21. So there was all my different possibilities, right? So what I'm going to do on my little table here is I'm going to just do these by 21s. Okay, I'm going to have my A, my B, my C, and my D, and this is going to be 2 21s, and this is going to be 4 21s, and this one's going to be 6 21s. You guys probably can write in there a little better than I can with these giant markers. So the A was all the way up here at 7. The B was at 3. The C was all the way up here at 6. And the D was at 5. Alright. Hopefully you guys had something that looked like that. If not, go back, try it again. Put some more time into it. Alright, this is where the rubber meets the road, the binomial experiments. This is a tough stuff. First of all, there are n independent trials. Okay, remember independent and dependent, what we learned about? Independent trials. I think I'm missing a letter there somewhere. Not that with my bad handwriting you can actually tell, but I think I am. Independent. Oh yeah, there's an N right there somewhere. Independent trials. Each trial has only 2 possible outcomes: success and failure. Remember we talked about binomial being yes or no. That's all you got. The probability of success is the same for each trial because they're independent. You have that much probability for success. P, probability for success, and the probability for failure would be 1 minus P. So if I have a 25% success chance, I have a 75% no success chance, 1 minus 0.25. And here's the formula that you need to know. N trials. C. K, that's how many successes that you want right now. P, the probability of success, to the number of successes that you have, to the K. P to the K. Times 1 minus P, that would be failures, to the N minus K. That would be the number of non-successes that you would have. Alright, so let's see how that works in an actual problem. Here we go. A survey taken in your school found that 68%, that's an important number, that's your P number, P equals 0.68. Make a note of that somewhere. Of the students are not afraid to fly. Not afraid to fly. Suppose you randomly survey 5 students. Draw a histogram of the binomial distribution for your survey. The probability that a randomly selected student is not afraid to fly is 0.68. Because you survey 5 students, N must be 5. Because you're going to run 5 experiments, so N is 5. Now remember what the formula was. N combination K. Successes to the K. Failures to the N minus K. Okay, let's see if I can blow this up a little bit. It'll be easier for me to write if I can make it a little bigger. Get these guys out of here. Alright. So, we have 5 every time, 5 right here, little number 5. Okay? C. Alright. The first one, K equals 0, and then 1, 2, 3, 4, 5. I want 5 successes, and so on and so forth. Right? I have 0.68. That's my success rate every time, 0.68. If 0.68 is my success rate every time, what's my failure rate? Can somebody figure that out for me? What's my failure rate? Hopefully right now you're saying it's 1 minus 0.68, which is 0.32. My failure rate is 0.32, so I write that in every time. Alright. Okay. Now, remember, this number that's going to go right here is going to match up 0, 1, 2, 3 with my K's, the number of successes I want to have, because I want 0.68 to the 5 when I want 5 successes. And those two numbers have to add up to be 5, so if I want 5 successes, that means I have to have 0 failures. I want 4 successes, I have to have 1 failure, 3 successes, 2, and so on. Alright. Now I throw all of that in my calculator, and on this one I got 0.003, and this one I got 0.036, and 0.152, and 0.322, 0.342, and 0.145. Okay? Now, if I take all that information and I draw my histogram, on my histogram some things I want. First of all, 0. I want my 0. If I were to survey people, what's the chances I find 0 people that are not afraid to fly? And then 1, 2, 3, 4, and 5. Okay. On the side there, I'm going to go in, let's go in decimals this time instead of fractions because my answers are all in decimals. Let's go in like, let me draw those in there. Let's go like 0.1 right here. 0.1, 0.2, 0.3, 0.4 at the top. Okay. So let's see what I have. I have for 0 people, it was 0.003. Let's choose a different color here. Let's do green. Not go like Christmassy. 0.003 is really low, barely even a bar there. 0.036, barely even point. Remember that first one would be 0.05, so that's barely up there. 0.152 all the way up to here, it looks like. I might color it in if I want. 0.322, this looks to be one of the bigger numbers, so it's all the way up to here a little bit. I don't know why that did that, but alright. 0.342, almost to that line, and back down. And 0.145, so that's back down to here somewhere, pretty close. Okay, so first of all, some things. A skewed graph, right? Certainly not going to be a symmetrical graph. And some things that I could expect. If 68% of my people say that they don't like to fly, or they're not afraid to fly, then I could expect that 5 times 0.7, which is essentially 68%, is 3.5. I would expect 3 or 4 people to be my big numbers. Well, that's what ended up happening, right? 3 or 4 people ended up being my big numbers. So that ended up working out. That's what you're going to have to be able to do on the test. That is on the test. If I had to star that puppy right now for you, I'd put some stars on it. I'd say I know how to do one of those because that is on the test. My star's not sticking with it, is it? Alright, interpret binomial distribution. Get those guys out of here. Let's see what we got here. Interpret a binomial distribution. Use the binomial distribution in example 3. What is the most likely outcome of our survey? Alright, well the most likely outcome of that survey was 4. Right? See right here is 4. 0.3424, 0.342. Alright. What is the probability that at least 3 students are not afraid to fly? Well, that would be 0.322, right? So it says the probability is greatest would be 4. We just said that. outcome that 4 of the students, because that was 0.342. And then what's the probability that at least, important word right here, at least 3 students are not afraid to fly? Well, then I'm doing the probability of k equals 3 at least. So it could be 3, but it could be 4, and it could be 5. So that's an or statement. 3 or 5, right? 3, 4, or 5. So what I'm going to do is add up those 3 things, which would be 0.322 plus 0.342 plus 0.145, and I get 0.809, or an 81% chance that that's going to happen. So that's pretty good stuff. That makes sense. Alright, on this next one here, I want you guys to practice doing this, and I want to see your work. Show some work on this one. I want to see what you got. You do the same kind of distribution. You're randomly doing 6 families, so you got 6 C, whatever the choice is. 57% owned a pet, so 0.57 is your success. 0.43 is your failure. You're going to take all of those to those powers. I should see 6 different experiments here. I want to see you guys do it, and I should see a pretty good histogram when you're done there. And then you're going to answer, you're going to interpret that on number 3. All right, we will check in on that one tomorrow. Show your work.